I hope that by exploring that applet, you were able to see that as the number of rectangles, n, gets bigger and bigger and bigger, the left-hand sum and the right-hand sum both converge towards one another, and while they're doing that, they sandwich the area, the exact area under the curve in between them. So this leads us to want to be able to find areas under curves, because if we wanted to figure out the exact distance that that object traveled, I hope what that applet convinced you of is that that is the same as finding the area under the curve of x squared from 0 to 2. So now all you need to do is reach back to your days in geometry class and remember the formula that your teacher gave you for the area under a parabola. Oh right, they never gave you that formula, did they? They just gave you things like rectangles and circles and triangles. Too bad. So we don't have a way to find the area under any sort of interesting curve, like a sine curve or a log curve or 1 over x or x squared. So that's what we need to do now. So we're going to now focus on developing a way to do that. We will come back to that specific problem of the f of t equals t squared from 0 to 2, and we will get the exact answers to that in a little bit. But now we want to talk about the general method of doing this. So if you're a mathematician, all the motivation that you need is, I don't know how to find the area under a curve, I'd like to do it, that's it. If you want some more practical motivation, then I hope that's what these last two examples gave you. If you have any sort of rate of change, whether it's the rate of change of the object's position, in other words, its velocity, the rate at which oil is leaking out of a tank, the rate at which a population is growing, the rate at which the disease is spreading, any of these things, if you want to actually figure out the number of people who got the disease, or the number of people who were added or lost from the population, or how far the object went, or how much oil leaked out of the tank, all of those amount to finding the area under the rate of change curve. So that's what we want to focus on now. So these are called Riemann sums, as we mentioned before. They're named after the mathematician Bernhard Riemann, who lived in the 19th century. He has today what is definitely the biggest unsolved problem in math called the Riemann hypothesis. That's the holy grail out there for people to work on. So we've been working at it for a long time, as you can see. He's the one who stated that problem getting up towards close to 200 years ago. So suppose we want to find the area under a curve. And when we say the area under a curve, we really mean the area between the curve and the x-axis. So we're going to call that signed area because we're going to count below the x-axis as negative and above the x-axis as positive. We'll talk more about that in the pieces to come, and that should become clear. If a question just specifically asks you for the area, though, you'll always want a positive answer. And again, we'll see examples of doing this. Well, so we start by what we did earlier. We took our interval from 0 to 2 and we chopped it up into 4 pieces. So in general, if we're trying to look at the interval from a to b, let's chop it up into n equal pieces. We're going to call each of them delta x, delta again standing for difference or change in. And how wide should each of those pieces be? If I'm taking the interval from a to b, breaking up into n equal pieces, how wide should that be? What should I write here? The length of the interval is what? It's b minus a, and we're breaking it up into n pieces. So the width of each one of them is going to be b minus a over n, just as we did in the previous example. It was 2 minus 0 over 4. So here I've got some graph of f of x. And we're going to chop it up into these n pieces, and we're going to label the pieces. So the starting point A is called x sub 0. And then this one will be x1, x2, and so forth. So what should this last one be? This last one should be xn. And the one before it should be xn minus 1. And we are now trying to write the left-hand sum and the right-hand sum for this particular function. So if I were doing the left-hand sum, when I have the choice between the value at x0 and x1, which one am I supposed to pick? We're supposed to pick the value at x0. So the height of my first rectangle would be this. So the height of that rectangle is f of x0. And the width of every one of our rectangles is delta x. So I'm taking the height of the rectangle times the width. We go to the next interval from x1 to x2. We do the same thing. It's the left-hand sum. I choose the value on the left, f of x1, multiply by the width, delta x. And we just keep on going. And by the time we get to this last interval, where we have the choice between the value at x sub n minus 1 and the value at xn, which one should we be choosing? We should be choosing the value at x sub n minus 1. So this value here. Now I know this is all very abstract. The purpose of this is to come up with our general definition of a way to find the area under the curve, just like we did with the way to find the instantaneous rate of change or the slope of the curve. How would we do the right-hand sum? In the first case, we have the choice between the value at x0 and x1. We would choose the value at x1. So that would be f of x1 delta x. And then the next one between x1 and x2, we would choose f of x2. And we would keep going. And the very last one would be f of xn. And remember, for something that's coming up very shortly, most of these terms are repeats, right? So f of x1 delta x is in both of them. F of x2 delta x is in both of them. F of xn minus 1 delta x is in both of them. The only ones that aren't, this term is in the right-hand sum. This term is in the left-hand sum. Those are the ones that aren't repeats. OK, I left some space here intentionally because mathematicians hate to write things out to take a lot of space, as we hope we've convinced you of during the semester. So there's some shorthand notation for this, and it's called summation notation. So here's a brief aside on summation notation. We use this fancy Greek letter, capital sigma. You've seen lowercase sigma maybe in a statistics class. That's the one that looks like this. And why do you think we use sigma? Remember, why did we use delta? We use delta for difference. So we use sigma for sum, because it's the Greek letter that sounds like our letter S. So what this sigma is saying is you start with k equals 1 in this particular case. Start with k equals 1 and plug it in. You get 1 squared. And then the rule here is that the k always goes up in increments of 1. So the next value of k is 2. So you plug in 2 there, and you get 2 squared, and then you get 3 squared, and you keep going until you reach this. So we get to 99 squared, and then we get to 100 squared, and that's the end. So you can see this is a much shorter way of writing out this whole thing. Now, just to be clear, this doesn't actually help you in any way in actually adding them up. It's just a shorthand way of writing it. Let's try to do the opposite. See if you can come up with a sigma notation, summation notation formula for this. And I'll warn you, there's infinitely many correct answers for any of these. So here it all seems like it's 5 over something. So 5 over what? So often when I give this problem in class with a bunch of people out here, somebody will say something like k plus 2, because we're going over by 2's here, right? And then they'll have to say, well, what should k start at here to get us a 7? K would start at 5. So let's see if this works, in case any of you at home were thinking something similar. So k equals 5. We plug in 5. We get 5 over 7. Great. Now, what's the next value of k? Remember, k always increments by 1. So the next value of k is 6. So we get 5 over 6 plus 2, or 5/8, which isn't what we wanted. So this did not work out. Because here, when k goes up by 1, the denominator also goes up by 1. We really want, when k goes up by 1, we want the denominator to go up by how much? We want the denominator to go up by 2, right? So you think to yourself, what would how can we make a function? How can I write a formula so that when k goes up by 1, the denominator goes up by 2? I hope you're thinking about a linear function with a slope of 2. So I could put something like 2k down here now. And what would we need to put? Well, it's up to us now to decide. So one way to do it would be to start with k equals, say, 0. And then my first value, then I'd have to put a 7 there. So if k equals 0, I plug in. I get 5 over 7. Looks great. Next one, k equals 1. I plug in. 2 times 1 plus 7, that's 9. That's great. And then what's the very last one? I need to plug in something so that 2k plus 7 equals 1001. So I think that would mean 2k equals 994. So k equals 497. And let's check if we plug in 497 here. When we 2 times 497 plus 7, I think does give us 1001. So this is just a way to get us understanding the sigma notation so that now we can use it over here. So it's useful when we're adding up a whole bunch of things that look the same. So here we're adding up perfect squares. Here we're adding up things of the form 5 over odd integers. So these are perfectly suited for sigma notation because we keep adding up things that look the same. All we're changing is the subscript on the x here. So I can write this. They all take the form f of x sub k delta x. And all that's different between the left and the right-hand sum is where k starts and stops. So in the left-hand sum, where should I be starting k? We want to start with f of x sub 0, so we want to start at k equals 0. And where do we stop? When k equals n minus 1. Similarly, down here, we're also doing f of x sub k delta x, except now k starts at 1, and k stops at n. So this is the left-hand sum, this is the right-hand sum, written in a nice compact notation using the sigmas, which is going to lead us to the notation for writing the exact area under the curve in a little bit. But what we want to talk about now is this question about what happens as n gets bigger and bigger and bigger and bigger. What happens as n goes to infinity? So in the applet that you just did, as I said at the start of this segment, we hope that you saw that as n got bigger and bigger and bigger, the two different sums converged. So the next applet that we have for you is to look at this difference, the difference between the right-hand sum and the left-hand sum as n goes to infinity. And before you even try the applet, ask yourself, what do you think this difference should go to as n goes to infinity, given what you saw in the previous applet that the right-hand sum and the left-hand sum seem to be approaching one another? So go ahead and give that applet a try, and then we'll come back and talk about it.